Okay, this is section 4.1, linear functions. Today we're going to be doing a bunch of application problems, and all of these application problems can be modeled with a linear function. So we're going to go into three different types of linear functions, and then the second part of the lesson is going to be to find the line of regression, a line of best fit for a certain set of data. So you're definitely going to need your calculator with you. Okay, so if you read example 1 here, it says a piece of machinery has an initial cost of $62,000 and a scrap value of $4,000 at the end of 8 years. The reason why we know this is a linear depreciation function is because it tells us find the linear depreciation function and then interpret the values. But it might not always say that in the problem, so you have to realize and recognize that you have a linear depreciation because you have an initial cost here. It's much more expensive than its value at the end of a certain amount of time. So this could be used for explaining, a car's value, all sorts of different things. But basically, this is the model that you're going to follow over here. So the value in terms of t, so value as a function of time, is equal to the depreciation rate, which is your slope, times your input, the number of years, plus some initial cost. So b here represents your initial value. Initial value when you first purchase it. So in this case, what I need to do is figure out what my slope is. So I know that I have actually two coordinates here. When time is 0, so when I first purchase it, it's worth $62,000. After 8 years, it is now worth only $4,000. So I'm going to find the slope between these 2 points, and after I calculate this, so 62,000 minus 4,000 over 0 minus 8, I end up with negative 7,250. So this is your slope. Really what this negative means is that you're decreasing in value. Okay. So my function then, my value as a function of time is equal to negative 7,250 t plus the initial value 62,000. So this is the function that models this situation. And again, this represents your initial value when you first purchase that piece of machinery. And this negative 7,250, our slope, represents a depreciation rate. It's a constant rate. You're changing by 7,000, it's basically dropping in value $7,250 every year. So you drop in value $7,250 per year. And actually, I shouldn't have a negative there. Let's just do money, so the units is dollars. So the drop in value of $7,250 a year. So that would be what our slope represents. Okay, so that's what it means by interpreting the values, just knowing what each part of your function represents. All right, now the second application problem you'll see is a cost function. So here it says the cost for the Chicago Tribune for Sunday home delivery is approximately 53 cents per newspaper with fixed costs of $1,070,000. We're going to write an equation that relates the cost C and the number of copies delivered. So the cost is going to be a function of the number of copies delivered. Okay? So over here, what we're going to use is this model here. And it's very similar to the value function. It's almost exactly the same, except for the slope now means it's the marginal cost. So this is a vocabulary term that you're going to need to be familiar with. If we ask you for the marginal cost, we're just asking for how much does it cost the company or whoever's making a product to produce one more unit of that product. So we start with our fixed cost. They don't pay $1 million, dollars every single time they produce a newspaper. What they're paying every single time they deliver that newspaper is 53 cents. Okay, so we already have a marginal cost. We are given that right here in 53 cents. So I didn't have to solve for anything here. I don't have to figure out what the slope is of this function. It's just going to be 0.53x. This is our slope, and then it's a function of x, right? And then our fixed cost here, this 1,070,000, is the one-time fee that they have to, the initial cost for, I don't know, starting up the business or whatever. They're assuming that this is a one-time fee. So this was our function here, pretty straightforward. Just make sure that you understand the vocabulary terms here, that you have your B value here is your initial startup cost. So it's very typical that you're going to see a one-time fee represented here as your starting amount. All right, last one is the rate function. And your rate function is really something that you've already done probably a way long time ago when you did like distance equals rate times time. So this is the idea that we're using here. We're going to take distance as a function of time, and your slope is going to represent a constant rate of change in this case. So we're assuming that we have constant velocity, so no acceleration like we did before when we had the distance problem with finding the average rate of change. This time we have a constant rate of change. We're not finding an average. It's just assuming that we're driving at a constant speed, in this case of 50 miles per hour. So we're going to take that idea of distance equals rate times time and just plug it in right into our model here. Notice that 0 is our initial value, and the reason why it's 0 is because when you're starting your trip, you haven't moved anywhere, so your initial distance is 0. So we just have the distance in terms of time is equal to 50t, and then plus 0. Obviously we can leave that off, but this would be the model that would define this function here. Again, make sure you know these vocabulary terms: the depreciation rate, your marginal cost, and the rate of change in this case is our constant velocity. Alright, now you're going to need your calculator out, so go ahead and grab your calculator so we can start with the second portion of our notes. Okay, so we're going to be doing a linear regression using this problem here. It says the chart below shows the world records for the men's mile run between the years 1911 to 1993. So we're going to enter the data here as the year that they broke the record and their time. Okay. Make sure you also notice that it says let t equal 0 represent the year since 1900. So in this case, when we have to input our data here, the year 1911 and the time here, let's put this in seconds actually too, so time is going to be in seconds. We would have 11 comma 255.4. Okay, so that would be your data. Now I only want you guys to actually do the ones that I've highlighted here on your worksheet, so I'll just highlight these as well. I only want you to input this data here into your calculator. So if you already know how to do this, if you remember from last year how to do a linear regression, you're more than welcome to input this stuff and then answer the questions that follow down here. So that's really what the most important part is, though, is answering these questions. And if you understand the difference between extrapolation and interpolation, then you're pretty much done with this lesson. If not, then I'm going to go through and explain how to do this on your calculator. Okay? Okay, so the very first thing that you're going to have to do here to prepare your calculator for the linear regression is to make sure that your calculator is formatted correctly. So on your calculator, make sure you hit Stat and then Setup Editor 5, and then hit Enter, and once it says done, you're good. Now we'll go to your catalog, so that's second 0, and you guys can take a look at my key press history. Second 0, and then scroll all the way down. I'm not going to do this because it will take me a long time on the calculator to scroll all the way down, but you want to go to Diagnostics On, okay, and then hit Enter. So this is just a one-time thing. I have all of these steps actually in your notes too, so you can flip over to these if you ever get confused or lost on how to do one of these problems, but all of the rules are just set up right there for you. So you only have to do this one time. After that, you won't have to do this anymore, okay? Alright, so let's get started with entering our data. Okay, so to enter data into the list, you're going to go to your Stat button here, because we're dealing with statistics. That's kind of how I remember it. Everything's going to be found in your Stat button. So go to Stat and then hit Enter on Edit, because you're going to edit these lists, and you're going to enter your data here. So your X column can go into list 1, your Y column will represent your L2. So I think the first point was 11, and then you can successively do all of your X values, but I'm going to scroll over and just do the first point, 255.4 I believe was the time, and hit Enter. Now if you want to clear any of the data that you already have in here, you're just going to scroll all the way up to L2 and then hit the Clear button and then Enter. Okay. I also have all of the data already done for you. So make sure you're entering these data points here. So pause, write all those down, and then enter these into your calculator. Okay? So one of the reasons why I picked just these 5 data points was, one, I didn't want you to enter all of this stuff in your calculator. That's a lot of data points, and you get the point after just doing 5 of them. But also because there's some kind of cool stories that go along with some of these runners here. Glenn Cunningham, for instance, from the U.S., he broke the record in 1934, but when he was 8 years old, I think he broke it when he was in his 20s, but when he was 8 years old, he actually was in a fire. He had the job, him and his older brother had the job of going to their one-room schoolhouse and lighting a fire so that it was warm, for when the students all got there. And one day, instead of it being filled with kerosene, it was filled with gas. So, it was a mistake. Somebody must have filled it, and when they lit it, it like sparked and blew up on him, and the whole schoolhouse burned down. His brother passed away. He made it, but he was so badly burned that the doctors, one, didn't think he was gonna make it, but also when he was kind of stabilized, decided that he should have his legs removed. And because he begged his parents not to let them do that, they refused and kind of nursed him back to health. And he ended up, being in a wheelchair, having to learn how to walk all over again. And then the guy goes ahead and, breaks the world's record for the mile run, which is pretty unbelievable and awesome. And then Roger Bannister, this guy had some, he was actually I think he was a med student at the time. So he was an Oxford medical student, and the whole medical community, if you kind of look at all these data points from, there had been years and years of, trying to beat the world record in under 4 minutes. So they kind of, in the medical community, decided that it was widely accepted that the human body was it was impossible to break the 4-minute barrier. So he ended up doing a lot of testing on himself. He developed a lot of training techniques and, testing to try to maximize his ability to run and break this record. And so I think it's kind of funny that, a doctor ends up, going against the whole medical community and saying, no, I'm going to be able to do this. So I think that's pretty cool. But anyways, you're going to enter this data. So let's go back to the calculator. And I have that data already entered. All right, so there's all the data entered here. And now we are going to graph that. So when you're graphing, you're going to hit second Y, which is the stat plot. So right here. And we want to turn this on. So see how right now my stat plot's off. I also have L1 and L2. That's the ones, the lists that I entered into. You can change those lists to L1, L3, if you have other data that you're entering. But we're going to keep it on L1, L2. So just hit enter to turn it on. Okay, and now if you want to go graph this, your data points, you're going to hit zoom. And I want to go to zoom stat because I just entered all those statistics. So I'm going to go to zoom 9 stat, and now I see all of those points plotted. Okay, so you can kind of see that this is going to be a linear function here. It's going to be best modeled by a linear function and with a negative slope. All right. Okay, so now we want to find, the line of best fit. We want to find a linear function that models this data. So what we're going to do is go to stat, and we're going to calculate this time. So click over to calculate the linear regression. Okay, so you're going to go down to 4 linear regression, hit enter on that, and I have list 1, list 2. We're going to hit enter on this, and where it says to store your regression equation, you're going to go to vars. And we'll scroll over to y1, or sorry, yvars, hit 1 on function, and y1, enter. So now it's going to store that linear regression model into my y equals. So right now there's nothing there, but after I hit enter back on here, oops, I got to go do it all over again. So let's go to stat, calc, linear regression, so 4. Scroll down to here, and we're going to click vars, yvars, enter on function, y1, hit enter, and now you're going to see it calculating your linear regression. Okay, so it's popping out, and like I said, if I go back to my y equals, I'll be able to see this now. It's inputting that function directly into my calculator for me. So anyways, let's go back to that screen where it had the, there it is. Okay. So I have, my A value here is the slope of this line, negative 0.381, b 258.9. So let me drag this into here. And I also have the correlation coefficient, which we don't really ask you much about this at all. You probably did this last year in 90s, but we don't really ask you much about the correlation coefficient. What we're interested is, whether or not you can use your calculator, graph this stuff, and then answer some questions that pertain to the particular model. Alright, so let's go back and, like I said, it's already stored in our y equals, so if I hit graph now I should see a line entering through those data points. Okay? So that's your linear regression model. So now you've got your equation. Now we're going to use that to answer some questions. So please make sure you're comfortable with doing all of these functions on your calculator. If you're not, go back to those. You can obviously rewatch this video, but also there's those directions. The note sheet that has the directions all listed out for you, and you can just use that as you're working through the problems in class. Okay, now let's go back to the note sheet and fill out some of those questions that accompany this model. So this is really what you're going to be tested on, is making sure, one, that you can use your calculator, but then also that you can actually answer some questions that pertain to the particular model. So here first says to just list the linear regression model, and that's going to be y equals negative 0.381. Oh, it says to the nearest hundredth, so negative 0.38x plus 258.91. Alright, so this is our linear regression model. Now, we are asked next to use a sentence to explain what the slope means. Now, a lot of students get tripped up on this, but all you want to do is think about what you defined your x and your y to be. Remember, we said x was the year after 1900, and y was equal to the time in seconds. So slope is your change in y over your change in x, right? Well, that means we're taking the change in our time over the change in years after 1900. So in this case, if I have negative 0.38 over 1, I'm going to read this as every, the time drops 0.38 seconds after, or every year after 1900. So there's a 0.38 second decrease in time every year. And of course you could switch that up a little bit and say, like, every year there's a 0.38 second decrease in the world record time. But basically I just did the y first and then the x. Alright? Now, you're also going to be asked to use the model to calculate certain things. Like here it says, according to the regression line, what would the record be in the year 1980? How accurate is your answer? So let's take a look at 1980. Well, when I'm inputting 1980, I'm going to let x equal 80. Right? This is what that's saying. They're giving me an x input, they're asking me for the y. So I'm just going to plug that right into my calculator. Negative 0.38 times 80 plus 258.91. Oops, 258.91. Now, there's a way to do this on your calculator also without having to type in anything else. If you want to use the exact model that you already have, you can store a value. So we said 80 was our the number we're going to plug in for x. So we're going to say 80, and I'm going to hit enter, and then I'm going to store that. Do you see this stow? It's kind of ghetto for store. Stow. And then let's store that as x. So, whoops, did not mean to do that. I'm trying to store that answer as x. So hit x here, just hit that button, which represents x. Enter, and now I've got that in as 80. So now, when I want to calculate that using my linear regression model. Alright, so remember how we put into our vars in our y1, we had scrolled over the function and we hit enter, and we have y1 listed as, if I go back to here, right here, this is our function. Well, now when I go back to vars and I enter y1 and I hit enter, it's going to calculate that function using our input of 80. So we end up with 228.41. So this is more accurate than when I used our rounded answer. But 228.41 is supposed to be the number of seconds that it took to run that mile in the year 1980. So let's go back and just check to see how accurate that data is. If I look at 1980, that's pretty much right on the money. We are just 0.4 of a second off, I think. So that's pretty much right on the money. Now, the next few questions, you're going to see that your answers are a little bit crazy. So it says, according to the regression line, what would the world record time be in the year 2575? So this time we're going to let x equal 675. So now I'm going to type in 675, hit enter, and then I'll store this. So stow, and let's store that as x. Now I want to bring back up the y1. Instead of having to go back to the vars and scrolling over, I can do second entry, and it'll bring up, I just keep doing that until I find where I had y1. So it's kind of cool, you don't have to re-enter all of that information. I don't know if anybody's ever shown you that trick, but when I hit enter, I get 1.6 seconds. Okay, so I get y equals 1.6 seconds. Now, that's pretty much crazy, right? Like, I don't think the human body, I know they talked about the 4-minute mile being impossible to break that barrier, but I don't really think that in the year 2575 the human body will be running the mile in 1.6 seconds, unless, you know, we're being teleported. But so this model isn't really working now, you're noticing, for numbers that are outside of our data set. When you try, you know, this next question says, according to your regression line, how fast would a caveman living around 350,000 years ago run the mile? Let's just let x equal negative 350,000. I know that's not really that accurate, and I'm not even sure if cavemen were living around then, but let's say they were cavemen living around then. So I'm going to enter negative 350,000, hit enter, and store that as x. Alright, second entry until I get the y1 again. There it is, hit enter, and I get a huge number. Alright, so let me see if I can write that down. I don't remember what it was. 3677.26 or 27. Okay, so this is saying it would take 133,000 seconds for them to run the mile when there were cavemen, you know, living around then. So this number obviously should strike you as odd, because that's what, 2,227.95 minutes. Okay, now if a caveman literally took that long to run a mile, then I don't even know how our species would have survived or made it, because that would mean they're walking pretty darn slow. Okay, so this is where we get into the idea of extrapolation and interpolation. Remember when we suggested that, you know, find the value when it was 1980, we were right on the money. It was like 0.4 seconds off, 0.4 of a second off. When we did extrapolation, though, which we're taking numbers outside of our data set. So this is what we had entered, right, for x. Well, look at our data points. All of our data falls within 1911 to 1993. So when we're interpolation is just taking values inside of your data set. Well, we get a pretty accurate, you know, account of what it should be. When we take values that are way outside of our range of data, though, that's called extrapolation. Now we get into, like, it's not as safe to just, you know, use our linear regression model, because again, it's just a model. It doesn't necessarily mean it has to be true, but when you're extrapolating data, you're going to get values that seem kind of outrageous the farther out you are. So obviously 1.6 seconds is way off, and so is this 2,227 minutes. Okay? Alright, that's the end of the lesson. Hopefully you are very comfortable with using your graphing calculator. Nice job.